Problem 525. An ideal gas mixture contains 35% helium, 20% methane, and 45% nitrogen by volume at the pressure of 2 atmosphere absolute and the temperature of 90 degrees of the centigrade. Calculate the partial pressure of each component, calculate the mass fraction of methane, calculate the average molecular weight of the gas, and calculate the density of the gas. To calculate partial pressure of helium, methane, and nitrogen in our problem, we need to look at the Dalton's law of partial pressure, which says that the partial pressure of helium in this case would be equal to the mole fraction of helium times the total pressure of the system, and Amgat's law of pure component volumes, which says that the volume of helium would be equal to the mole fraction of helium in our reactor. So these two laws are interchangeable, and because the problem says that we have percentages of 35, 20 and 45 on the volumetric basis, we can automatically assume that this would be a molar basis approach here. So the partial pressure of helium would be equal to the mole fraction of helium, which is 35% times total pressure. That partial pressure would be equal to 0.7 atmospheres. For the methane, partial pressure of methane would be equal to 20% of methane times 2 atmospheres, 0.4 atmospheres. And the partial pressure of the nitrogen, since we have 45% of the nitrogen on the volumetric basis or the molar basis, times 2 atmospheres would give us 0.9 atmospheres. For part B, where we have to calculate the mass fraction of methane, we would have to convert the molar fractions of each of these components, or if the question is reference to methane, we can focus on the methane here. So the volume fraction of methane is 20%, so the molar fraction of methane is also 20%, and again we go back to the Amgat's law and Dalton's law. Assuming that we have 1 mole of the gas, we would have 0.2 moles of the methane, and if we multiply the mole fraction of methane by the molar mass of the methane, we would end up with mass of the methane in our reactor, which is equal to 3.21 grams. For the other components, for helium and for nitrogen, the masses of these two components would be equal to 1.4 grams helium and 12.61 grams of the nitrogen. The total mass of the mixture would be equal to 17.22 grams. The question asked is calculate mass fraction of methane in our system. So from the previous calculation we know that we have 3.1 grams of methane divided by the total mass of the components in the reactor, and this ratio would give us 18.6%. Question number 3, calculate the average molecular weight of the gas. So the average molecular weight of the gas would be equal to the grams of the gas, which we have calculated before, 17.22 grams. And since we have 1 mole in our reactor, that molecular weight would be equal to 17.22 grams per mole. The last question is calculate the density of the gas. And to calculate the density of the gas, we have to look at the ideal gas equation. And as we derived this equation during the lecture, the density of the gas would be equal to the ratio of the pressure times molar mass of our mixture divided by the gas constant R times temperature. When we use these numbers and apply this ideal gas equation, our density of the gas would be equal to 1.15 kilograms per cubic meter.